Time may not flow in just one direction. Physicist Julian Barber famously said time is an illusion, albeit a very persistent one. This journey through 28 forgotten theories about time's direction will completely reshape how you see reality. You will discover why brilliant ideas about time were abandoned and what they could reveal about the universe's deepest secrets. What if the past and future are happening at once, or consciousness itself creates the flow of time? By the end, your understanding of cause and effect, memory, and even your own free will might be turned inside out. Are you ready to question everything you thought you knew about time? Ludwig Boltzmann died by his own hand, a tragedy born from the weight of an idea too revolutionary for his time. He was convinced that the relentless forward march of time was not a fundamental law of the universe, but a grand and persistent illusion. His reversible time hypothesis rests on a single, powerful concept: entropy. Think of entropy not as decay, but as disorder. A new deck of cards is perfectly ordered, its sequence predictable. Shuffle it once, and it becomes slightly more disordered. Shuffle it 1,000 times, and the cards reach a state of maximum randomness. The universe, Boltzmann argued, started as that pristine, ordered deck, a state of incredibly low entropy. Everything that has happened since, from the birth of stars to the firing of your own neurons, is just the universe shuffling itself into disorder. This is why we remember the past and not the future. The past was more ordered, but here is the radical twist. Boltzmann proposed that given an almost unimaginable amount of time, the random dance of particles would, by pure chance, eventually stumble back into a state of order. A thermal fluctuation would cause entropy to spontaneously decrease, and for a pocket of the cosmos, time would appear to run backward. Cause and effect would invert. A shattered glass would reassemble on the floor and leap back into your hand. Memories of tomorrow would feel as real as memories of yesterday. This is not mere philosophy. Modern thinkers like Sean Carroll have resurrected this idea, suggesting that if the universe is truly eternal, these fluctuations are not just possible, but inevitable. They would give rise to isolated pockets of order, even spontaneous conscious minds dubbed Boltzmann brains, observers who flicker into existence from the chaos, complete with false memories of a past that never was. This forces a deeply unsettling question. If time can reverse, then the solid ground of causality we walk on every day begins to crumble. Your decision to press play on this video might not be the cause of you watching it, but the effect of a future state pulling backward through time. Your sense of free will, the feeling that you are steering your life, could be a side effect of the particular temporal perspective you happen to occupy. Are we, like Boltzmann himself, simply trapped by a perspective, unable to see the timeless whole? The answer might lie not in the cosmos, but in the very nature of the mind observing it. While Boltzmann saw time's flow as a statistical illusion, another brilliant mind found it to be the very heart of reality. Alfred North Whitehead would often stroll through the Cambridge Gardens, his thoughts turning over a radical idea. What if the universe is not made of static things, but of dynamic, unfolding events? This is the core of his process philosophy. Reality, he argued, is not a collection of substances like particles or rocks, but a continuous flow of processes. In this view, time is not just a dimension we move through. It is the fundamental fabric of existence itself, an active becoming. Each new moment does not simply follow the last, it actively creates the next through a process Whitehead called concrescence. Think of a conversation. Your response is not just a reaction to my words. It is a new creation that absorbs the past moment and brings something novel into being. That is concrescence, the birth of a new actuality from the influences of the past. And those influences are real and objective. Whitehead called them prehensions, the way each new moment physically feels or grasps the moments that came before it. Your present experience is quite literally prehending the entire history of the universe, feeling its weight and its possibilities. This is a universe alive with interaction, where the past is not gone, but actively ingredients the present. Contemporary physicist Lee Smolin has found a surprising resonance between these ideas and his work in loop quantum gravity, suggesting that time itself might be more fundamental than space. This stands in stark opposition to Einstein's block universe, where all of time simply exists at once. For Whitehead, the future is genuinely open, not yet written. It is created, moment by moment, through our decisions and the interactions of everything in the cosmos. This is a world where your choices are not illusions, but real creative acts that weave the ongoing story of time. If time is such a fundamental and active process, then we must ask what happens when we probe its very smallest scales, in the strange and probabilistic world of quantum mechanics. But when we leave the human scale of process and enter the bizarre quantum realm, our classical understanding of time dissolves entirely. Two particles are created together in a lab, then sent flying to opposite ends of the galaxy. Despite the immense distance, they remain mysteriously linked in a state called quantum entanglement. A measurement performed on one instantly influences the state of the other. This spooky connection, as Einstein called it, might be more than just a strange quantum quirk. Austrian physicist Czeslaw Bruckner proposed a breathtaking idea. What if time itself emerges from these very quantum correlations? In his radical framework, the flow of time is not a fundamental stage on which events play out. Instead, it bubbles up into existence when quantum systems become intertwined through interaction or measurement. Think of it like this. A single, isolated quantum particle has no sense of time. It simply exists in a fuzzy cloud of possibilities. But when a second particle becomes entangled with it, a kind of clock starts ticking. The correlations between them create a sequence, a before and after. This is not just a metaphor. Experiments with quantum clocks have demonstrated something astonishing. For a pair of entangled particles, time can literally flow at different rates. The temporal order of events, what happens first and what happens next, becomes relative, a property not of a universal clock, but of the specific quantum relationship. This provides a profound bridge between the warring giants of modern physics, quantum mechanics and Einstein's general relativity. Bruckner's work suggests that spacetime itself, the four-dimensional fabric of the cosmos, might emerge from a deeper, more fundamental network of quantum relationships. If this is true, then the arrow of time, the reason we see entropy always increasing, might be a direct consequence of the universe's quantum correlations growing ever more complex and widespread since the Big Bang. The one-way street of time could be a side effect of the cosmos becoming more deeply and intricately entangled with itself. So if the very fabric of time is woven from quantum connections, what does that say about the universe as a whole, and the grand cosmological story it tells? John Wheeler's universe is one where the present reaches into the future, and the future reaches right back. His famous delayed choice experiment reveals this strange dialogue across time. Imagine a single photon, a particle of light, traveling through a laboratory apparatus toward a screen with two slits. Common sense says the photon must choose one path or the other. But in the quantum world, it behaves as if it travels through both paths simultaneously, creating an interference pattern, a signature of its wave-like nature. Now for Wheeler's twist. What if, after the photon has already passed the slits, but before it hits the final detector, a scientist suddenly chooses to insert a device that reveals which path it took? In that instant, the photon's behavior changes. It acts like a single particle that took one definite path, and the interference pattern vanishes. The staggering implication is this. A decision made in the present appears to rewrite the history of that photon. An event that already happened, its journey through the slits, is altered by a choice that had not yet been made. This is the heart of Wheeler's participatory universe. He proposed that reality does not exist in a finished state, independent of us. Instead, it comes into being through the act of observation. We are not merely spectators on a cosmic stage. We are participants, and our measurements help solidify what is real, even across time. This process creates feedback loops, where future observations influence past events. The flow of time in this view is not a one-way river but a constant, bi-directional conversation. The past sets the stage, but the future has a voice in how that stage was built. This idea of retrocausality, where effects can precede their causes, finds startling support in modern quantum eraser experiments. In these setups, information about a photon's path is first recorded and then later erased. When the information is erased, the photon seems to revert to its original, wave-like behavior, as if the act of erasing the future data reached back and changed the photon's past decision. It is as if time itself is checking its work, allowing for revisions. If Wheeler was correct, then the universe requires observers to bring its history into sharp focus. The Big Bang did not create a fixed, unchangeable past. Instead, the past is a tapestry still being woven with threads pulled from the future. Your act of observing the world right now is not just witnessing history. You are participating in its final creation. This elegant symmetry, where future and past collaborate, resonates deeply with the next great puzzle of time, a principle that demands this beautiful balance in the very laws of physics. While Wheeler saw time as a conversation, other physicists proposed it might be a journey along a hidden path. In 1926, Stockholm, Oskar Klein was grappling with a theory that would stretch the very fabric of reality. He was refining the work of Theodore Kaluza, who had a breathtakingly elegant idea. What if our universe has not just 3 dimensions of space and 1 of time, but a secret 5th dimension? Klein's genius was to ask a simple, profound question: where is it? His answer was that this 5th dimension is not a vast, empty space we can travel through. Instead, it is curled up into a circle so infinitesimally small that it is completely hidden from our view, a concept known as compactification. To understand this, picture a single, impossibly long garden hose stretching to the horizon. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl on its surface, you would discover a second dimension, the circular path around its tube. Klein proposed our reality is like that. We are the ants, unaware we are moving on a 5-dimensional cylinder. In this framework, every fundamental particle is not a point, but a tiny vibration looping around this hidden dimension. And here is where it gets truly strange. What we perceive as the relentless, one-way flow of time might simply be our limited perspective of a grander, multidimensional reality. The past, present, and future could all coexist as fixed points along this coiled 5th dimension, with our consciousness just tracing a single, linear path through it. This leads to one of the most elegant speculations in all of physics. What if antimatter, the mysterious mirror of ordinary matter, is simply normal particles moving backward along this hidden dimension? A positron, the antimatter counterpart of an electron, would not be a different kind of particle, but the very same electron traveling the opposite way around the microscopic circle of the 5th dimension. This could elegantly explain one of the universe's great mysteries, the matter-antimatter asymmetry. Perhaps the Big Bang created a slight preference for matter to move in one temporal direction over the other. Klein's compactified dimensions are not a forgotten relic. They form the bedrock of modern string theory, which suggests there are not 1, but 7 hidden dimensions curled up at the heart of every point in space. This multidimensional reality forces us to confront a dizzying possibility. If time has more than 1 dimension, then our conscious experience of a single, linear past might be the ultimate illusion, a mere shadow on a cave wall cast by a reality of unimaginable complexity. Henry Bergson watched an ice cube melt, not as a physicist tracking temperature, but as a philosopher witnessing a profound mystery. He saw in that slow drip a reality that clocks could never capture, a process he called duration. For Bergson, the scientific time of minutes and seconds was a lie, a convenient fiction we created by chopping up the flowing river of existence into frozen, spatial slices, like individual frames from a movie. Real-time, la durée, is the movie itself, a continuous, indivisible stream of qualitative change where each moment is saturated with the memory of all that came before. Your own consciousness is the perfect example of duration. Think of a melody. You do not hear it as a series of disconnected notes, but as a whole, flowing experience where each tone bleeds into the next, its meaning carried by what you just heard and what you anticipate. Isolate one note, and the music dies. Bergson argued this is the true nature of time, a cumulative process where the past is not a gallery of finished pictures, but a living force that gathers itself, like a snowball rolling downhill, growing heavier and more layered with every moment of your life. This is why your sense of time is so fluid. In a moment of sheer terror, seconds can feel like hours, your mind processing a flood of sensory details in what a clock would call an instant. Neuroscientist David Eagleman's experiments confirm this, showing that during frightening events, your brain enters a state of hyper-awareness, recording so much rich data that upon recollection, the event feels subjectively longer. Time stretches and compresses not with the ticking of a clock, but with the intensity of your experience. Bergson believed we access this reality not through cold intellect, but through intuition, a direct feeling of being immersed in time's flow. If he was right, then the arrow of time is not just a property of the cosmos, but is woven into the very fabric of mind. Your conscious life is not a passenger on the river of time. You are the river itself, a constantly accumulating history that creates the undeniable direction from past to future. This deep connection between time and consciousness points toward an even more intimate relationship, one written into the biology of every living thing. Ilya Prigogine watched a chemical clock rhythmically pulse between two colors, a mesmerizing dance of order emerging from chaos. This was not a system winding down into disorder. It was a system building temporal structure, a clock that ticked with a life of its own. His revolutionary insight was that the arrow of time is not merely a grim reaper of order, but a potential architect of complexity. He called these systems dissipative structures. Think of a whirlpool in a flowing river. The whirlpool maintains its beautiful, ordered shape not in spite of the river's chaos, but because of it. It constantly takes in energy and matter from the flow and dissipates waste back out. It exists far from equilibrium, thriving on the energy gradient. This is the secret to time's creative power. Prigogine showed that far from the bland state of thermal equilibrium where nothing happens, complex systems can spontaneously self-organize. They achieve what he termed order through fluctuations. A small, random fluctuation in the system can be amplified by the flow of energy, kicking the entire structure into a new, more complex state of order. A star is a dissipative structure, drawing in hydrogen and radiating light and heat. A living cell is one, consuming nutrients and maintaining its intricate form. Your own body is a walking, talking dissipative structure, a temporary island of profound order sustained by the constant flow of energy from the sun. This reframes the entire story of entropy. It is not just a slow slide into disarray. The universe's overall disorder increases, yes, but that very process provides the driving force for local pockets of order to bloom into existence. Time's arrow, in this view, is the direction in which complexity can arise. Prigogine's work on non-equilibrium Thermodynamics suggests that the one-way flow of time might be fundamentally tied to the cosmos's inherent tendency to produce ever more intricate structures, from swirling galaxies to conscious minds. His ideas now echo in the most advanced realms of physics, where some quantum gravity theorists propose that time itself is not fundamental, but emerges from the complex relationships within a vast quantum system. The flow of time we feel may be the experience of the universe growing in complexity around us and within us. This profound link between time and rising complexity forces us to look back, to the very first moment, to ask what set this entire creative, irreversible process in motion. John Cramer's transactional universe begins with a handshake across time. Imagine a single electron poised to leap from one energy level to another. In the standard quantum view, its jump is a fuzzy cloud of probability. But Cramer proposed something far more concrete and profoundly strange. That electron does not simply vanish and reappear. Instead, it sends out a call into the future, a wave moving forward in time known as a retarded wave. This wave travels forth, exploring all possible paths to its destination. Upon reaching a potential absorber in the future, that absorber sends a response, an advanced wave that travels backward in time, carrying a confirmation of reception. Only when these two waves, the offer from the past and the echo from the future, meet in a perfect resonance does the transaction complete. The particle's journey becomes real. This is the quantum handshake, a negotiation between past and future that solidifies reality itself. Think of it like this. You decide to shout across a canyon. The sound wave travels out, and a moment later, you hear the echo returning. In Cramer's universe, every quantum event is like that shout and its echo happening simultaneously, with the echo arriving from the future to confirm the event ever occurred. This elegant framework dissolves some of quantum mechanics' deepest puzzles. The famous double-slit experiment, where a single particle seems to pass through two holes at once, is no longer a paradox. The particle's retarded wave travels through both slits, exploring all paths. The advanced wave from the detector then returns through time, selecting which path will be reinforced in the final handshake. The particle was never in two places at once. It was simply conducting a temporal negotiation. Even quantum entanglement finds a simple explanation. Two entangled particles are linked because their original transaction involved a single, unified handshake that binds their fates across space and time. Experimental support for this radical idea comes from modern quantum eraser experiments. In these setups, the choice to measure or erase a photon's path information happens after the photon has already been detected. Astonishingly, that future choice seems to retroactively determine whether the photon behaved as a particle or a wave in the past. For Cramer, this is not magic. It is simply the advanced wave from the erasure device traveling backward to complete a different transaction, rewriting the quantum history. If this interpretation is correct, then the one-way flow of time we experience is a statistical illusion. At the fundamental quantum level, time is perfectly symmetrical, a constant two-way street of offers and confirmations. Our macroscopic world appears irreversible only because certain transaction patterns become overwhelmingly probable, creating the emergent river of time we perceive. This vision of a universe built on temporal handshakes points toward an even deeper layer of reality, where time itself may be a geometric structure waiting to be unfolded. Kurt Gödel handed his friend Albert Einstein a universe that spun on its axis, a cosmos where time itself could tie itself into knots. The great mathematician had found a new and startling solution to Einstein's own equations of general relativity, one that permitted closed time-like curves. These are not mere loops in space, but paths through the fabric of reality that could carry you on a journey ending at the very moment you began. In Gödel's rotating universe, the entire cosmos whirls like a vast, silent carousel. This universal spin creates a cosmic drag, warping spacetime so severely that if you were to travel far enough along a certain path, you would not arrive at a different place, but at a time in your own past. There would be no single objective now. Your past could be my future, depending entirely on our paths through this spinning labyrinth. The most profound implication was this: time travel to the past was not a fantasy, but a mathematical feature of a possible reality, allowed by the very laws of physics Einstein had penned. Our universe, thankfully, does not seem to possess this overall rotation. Yet Gödel's work shattered an unspoken assumption. He proved that Einstein's block universe was not the only possible outcome of his equations. The river of time could, in theory, flow in a circle. This revelation opened the floodgates for other exotic structures, like traversable wormholes, which could act as shortcuts connecting different eras. But this immediately raises the specter of paradox. What if you traveled back and prevented your own birth? How could such a logical contradiction be resolved? Physicists like Kip Thorne have suggested that quantum mechanics might come to the rescue. At the microscopic scale, the laws of probability could simply forbid any sequence of events that leads to a paradox. A gun aimed at your grandfather might always jam. A vital piece of information might always be lost, ensuring consistency in the timeline. The universe would behave like a master editor, pruning away any branches of reality that contain logical impossibilities. This dance between the large-scale warping of spacetime and the probabilistic rules of the quantum world suggests that if time loops do exist, they are protected from chaos by the fundamental graininess of reality itself. Gödel's spinning cosmos forces us to consider that the one-way flow of time might be a local ordinance, not a universal law, and that information might not just move forward, but could also trickle back from tomorrow. David Bohm saw a deeper reality hidden beneath the surface of things. He was captivated by the hologram, a device where even the tiniest fragment of the film contains enough information to reconstruct the entire three-dimensional image. Bohm proposed that the universe itself operates on this same principle. He described reality as having two fundamental layers. The world we perceive, with its separate objects and linear sequence of events, is what he called the explicate order. This is the unfolded reality, the finished image projected from the cosmic film. But beneath it lies the implicate order, a vast, enfolded realm where past, present, and future all exist simultaneously, woven together in a unified whole. In this view, the flow of time is not a movement through a series of moments. It is the continuous process of unfolding, where aspects of the implicate order become manifest in our explicate reality, only to then re-unfold back into the deeper structure. Think of a single drop of ink slowly stirred into a viscous fluid like glycerin. As the stirrer turns, the ink becomes enfolded, hidden from view within the clear liquid. But if you reverse the stirring, the ink droplet perfectly unfolds, reappearing in its original form. Bohm saw the cosmos as that fluid, with every event and object simply an unfolded expression of the implicate whole. This framework elegantly incorporates quantum mechanics through his pilot wave theory. While standard quantum theory says particles do not have definite positions until measured, Bohm argued they do have real trajectories, guided by a subtle quantum potential field. This field is not a force in the conventional sense, but an information field that permeates all of space, shaped by the entire system. It is like an invisible ocean current guiding a ship, where the current contains information about the entire ocean's shape. The particle's path is determined, but the guiding wave is non-local, instantly connecting every part of the universe to every other part, just like the information in a hologram. This suggests our unshakable sense of time's arrow, of cause preceding effect, might simply be the way information becomes explicated from the implicate order. Your memory of the past is not a recording stored in your brain. It is a present moment unfolding from the deeper structure, a specific retrieval from the cosmic hologram. Your anticipation of the future is another kind of unfolding, a reading of the quantum potential's guidance. If Bohm was correct, then the solidity of time is an illusion of perspective. We are not moving through time, we are participants in an eternal process of revelation, with the entire history and destiny of the universe enfolded into the here and now. This holographic nature of reality, where information is fundamental, points directly to the next great puzzle, a principle that treats information not as a passenger on time's arrow, but as its very source. Walter Ritz stood almost alone against the rising tide of Einstein's relativity. In the early 20th century, he proposed a radical alternative, the emission theory of light. Ritz insisted that the speed of light is not a universal constant, but depends on the motion of its source, much like a baseball thrown from a moving train. This led him to a profound conclusion about time itself. He argued that electromagnetic forces only propagate forward, as what physicists call retarded potentials. These are waves of influence that can only move from the present into the future, never backward. In Ritz's universe, the advanced solutions of Maxwell's equations, which would allow effects to ripple backward in time, were mere mathematical ghosts with no physical reality. This fundamental asymmetry, he believed, was the true source of time's arrow, built directly into the fabric of electromagnetic interaction. A radio broadcast travels from the station to your car stereo, not the other way. The light from a distant star reaches your eyes centuries later. This one-way street of cause and effect was, for Ritz, not an emergent property but a foundational law. Though his specific theory was ultimately disproven by experiments showing light's speed is indeed constant, his core intuition has never fully faded. Modern physics, particularly in the study of charge, parity, and time vilation, reveals a subtle but real asymmetry in the behavior of fundamental particles, a microscopic arrow that may indeed be rooted in electromagnetic interactions. Quantum field theory, the most accurate framework we have, demonstrates that under certain conditions, particles overwhelmingly interact through retarded propagators, echoes of Ritz's original vision. His insistence that time's direction is written into the most basic laws of force continues to challenge us, forcing a deeper question. If electromagnetism holds a key to time's arrow, what secrets might be locked within the even more powerful force of gravity? Dennis Sciama looked up at the starry expanse and saw more than distant suns. He saw the very engine of time. His profound insight was that inertia, the resistance of an object to being moved, is not an intrinsic property. It does not come from within. Instead, it is a whisper from the cosmos, a gravitational influence from all the matter in the universe. This Machian principle suggests that the fixed stars are what anchor you to the ground, their collective gravity defining what it means to be at rest or in motion. Sciama then asked a breathtaking follow-up question. If inertia is a cosmic gift, then what about time's arrow? Could the relentless forward march of time also be a consequence of our gravitational relationship with the entire universe? He proposed that the gravitational field itself possesses a direction. As the universe expands, the gravitational potentials from distant galaxies are constantly changing, evolving in a specific, one-way fashion. This cosmic evolution creates a fundamental asymmetry in how gravity interacts with matter, an asymmetry we experience as the flow of time. The expansion of space is not just a backdrop for time, it is the very mechanism that winds the cosmic clock. This leads to a staggering prediction. If the universe's expansion were to halt and reverse into a great contraction, the gravitational potentials would begin to evolve in reverse. The cosmic tug from all matter would start to pull time backward. In such a collapsing universe, entropy would decrease, shattered glasses would reassemble, and memories would flow from the future into the past. The arrow of time is not an absolute law, but a cosmological contingency dependent on the fate of the whole cosmos. Today, Sciama's vision finds new life in the most cutting-edge theories. Some physicists, like Erik Verlinde, propose that gravity is not a fundamental force at all, but an entropic force. It emerges from the statistical tendency for a system to increase its disorder, much like the pressure in a gas. In this view, the force of gravity and the arrow of time are two sides of the same coin, both arising from the universe's deep-seated drive toward higher states of entropy. This profound link between the large-scale structure of the cosmos and the local experience of time forces us to look back, to the very first instant, to ask what initial condition could have set this entire irreversible process in motion. Thomas Gold saw the cosmos not as a one-time explosion, but as a breathing entity. His oscillating universe theory proposed an endless cycle of expansion and contraction, a cosmic heartbeat with a breathtaking consequence. Time itself would reverse direction at each turning point. In this grand vision, the Big Bang was not the absolute beginning, but merely the moment of maximum expansion from a previous collapse, a big crunch. And as the universe began to contract, the arrow of time would flip. From our perspective, it would seem the entire cosmos was running in reverse. Radiation would not stream out from stars, but would instead converge upon them, pumping energy back into their cores. Heat would flow from colder objects to hotter ones. Shattered vases would rise from the floor, their fragments leaping back into a perfect whole. Information would seemingly emerge from the random jostling of particles, as disorder spontaneously gave rise to order. This elegant idea solved one of cosmology's most profound puzzles, the problem of low initial entropy. Why did the universe begin in such an incredibly ordered, low-entropy state? Gold's answer was simple and beautiful: it did not. The low-entropy state we call the Big Bang was actually the high-entropy end of a preceding cosmic cycle, viewed through a reversed arrow of time. The universe was reset not to order, but from order, with time flipping to make it appear as a beginning. While compelling, this breathing universe faces a modern challenge. Our observations show the expansion of the cosmos is not slowing down, but accelerating, driven by a mysterious dark energy. A perpetual cycle of crunch and bang seems unlikely if the universe is destined for an ever-accelerating expansion. Yet, Gold's core intuition, that the arrow of time is inextricably linked to the cosmological fate of the whole universe, continues to resonate. Some contemporary physicists have adapted his cyclical concept into a multiverse framework. Perhaps our universe is just one bubble in a vast cosmic foam, each with its own local arrow of time, its own direction of temporal flow. In some regions, time might run opposite to ours, while in others, it could be cyclical or even static. This vision of a multiverse with multiple time arrows connects to ancient philosophical ideas found in Hindu cosmology and Stoic philosophy, which envisioned time as a great wheel, eternally turning. Gold's breathing cosmos invites us to see our one-way street of time not as an absolute law, but as a local condition, a temporary current in a far vaster and more mysterious ocean. If time's direction can be tied to the universe's expansion, then what happens when we look not at the cosmos as a whole, but at the strange, singular points where its fabric is torn apart? Edward Arthur Milne was a mathematician who dared to rewrite Einstein's rules, not by adding complexity, but by proposing a fundamental duality at the heart of reality. In his theory of kinematic relativity, Milne argued that the universe operates on two distinct kinds of time. The first is dynamical time, the precise, ticking clock time that governs the motion of particles and planets, the time measured in our physics laboratories. The second is cosmological time, a grander, more universal rhythm that charts the evolution of the entire cosmos. In Milne's universe, these two times are not the same. They flow at different rates, and the entire history of the cosmos, from a hot, dense beginning to its present expansion, is a consequence of this divergence. The redshift of distant galaxies, which we interpret as evidence for an expanding universe, was not, for Milne, evidence of space itself stretching. Instead, it was a kind of cosmic time dilation, a natural result of the difference between how we measure time locally and how the universe as a whole ages. This framework elegantly built in a fundamental arrow of time. Cosmological time provided a master clock, a preferred direction that gave the universe a definite past and future, an aging process that imparted an irreversible flow to all events. While general relativity ultimately provided a more accurate description of gravity and cosmic evolution, Milne's core insight about multiple timescales has never truly vanished. Today, as cosmologists grapple with the Hubble tension, a puzzling discrepancy in how fast the universe is expanding, some wonder if the problem lies in assuming a single, uniform time. Could it be that our local clocks and the cosmic clock are subtly out of sync, just as Milne suggested? There are even proposals that the fundamental constants of nature, like the fine structure constant, might slowly change over cosmological time, further eroding the idea of a single, absolute temporal metric. This leads to a startling possibility. If cosmological time and dynamical time are different, then what about the time that governs the quantum realm? Could there be a third, even more fundamental time scale, a quantum time that operates by its own rules? Milne's forgotten duality opens the door to a universe where time is not a single river, but a confluence of many streams, each flowing at its own pace and direction, preparing us for the strange reality where time itself may be quantized. Herbert Dingle saw a crack in the foundation of modern physics, a paradox that threatened to unravel our understanding of time itself. He focused on the famous twin paradox of special relativity, where one twin rockets away on a high-speed journey and returns to find the other has aged more. Einstein's theory explained this through the traveling twin's acceleration, breaking the symmetry and providing a definitive answer for who was truly moving. But Dingle was not satisfied. He argued that if relativity truly held all motion as relative, then from the traveling twin's perspective, it was the Earth that sped away and then returned. Each twin should logically conclude the other was younger, a contradiction that acceleration alone, in his view, could not cleanly resolve. He believed this exposed a fatal flaw, suggesting that time was not a physical reality that could be stretched and compressed, but something far more subjective and perhaps even illusory. The scientific mainstream ultimately resolved the paradox within the framework of relativity, but Dingle's relentless critique forced a profound philosophical question. Is the time dilation measured by atomic clocks a real physical effect, or is it a consequence of our perspective, a kind of relational illusion? This debate echoes in the work of contemporary philosophers who argue that Dingle's concerns point toward a reality where time is not a universal river, but a network of individual perspectives. Your personal now and the now of someone in a distant galaxy may not align, and there may be no single, privileged clock governing the cosmos. This deep connection to subjective experience brings the mystery of time out of the cosmos and into the human mind. Dingle's emphasis on the lived experience of time finds a startling parallel in modern neuroscience, where our perception of duration can stretch and compress based on emotion, focus, and even body temperature. The physics of clocks and the psychology of time are not separate realms, but may be two windows into the same profound mystery, a mystery rooted in the very biology of how we perceive the world. Time feels solid and continuous, a single river carrying us from birth to death. But for scholar J.T. Fraser, this was an illusion crafted by our own minds. He saw time not as one thing, but as a series of distinct levels, a hierarchy of temporalities built up over the history of the cosmos. At the very bottom lies the realm of atemporality. This is the strange world of quantum events, where particles pop in and out of existence without a clear before or after. There is no flow, no sequence, just a fog of pure potentiality. From this timeless foundation, the physical universe of stars and galaxies emerges, a level Fraser called prototemporality. Here, time exists, but it is a weak statistical arrow. It is the time of thermodynamics and entropy, a direction defined by increasing disorder, but without a true past or future, only probabilities. Then, life arrives. With the first living cell, a new kind of time is born, biotemporality. This is time with a past and a future, a present moment defined by a goal, like finding food or avoiding danger. A bacterium moves toward a nutrient, its behavior oriented by a temporal horizon. Its clock is the rhythm of its metabolism, the cycle of its division. Finally, with the human mind, we reach nutemporality. This is the time of consciousness, of history, of the self. It is a time rich with memory and anticipation, where we can reflect on the past and plan for the distant future. We are not just in time, we hold time within us, weaving a narrative of our lives from countless moments. Your experience of watching this video, of following this sequence of ideas, is a perfect example of nutemporality in action. Fraser's profound insight was that these levels are not separate. They are nested, each one emerging from the one below through evolution. The psychological time of your mind is built upon the biological time of your cells, which is built upon the physical time of the atoms that make you up. Your unshakable sense of a flowing present is the result of your brain integrating these different temporal scales, from the millisecond firing of your neurons to the decades-long story of your life. This hierarchical view is helping neuroscientists today unravel the brain's complex timekeeping systems. How does a rapid neural oscillation relate to the slow formation of a childhood memory? Fraser's framework suggests they are different levels of the same temporal hierarchy, all woven together by consciousness. If time is such a layered structure, then we must ask what its most fundamental building blocks might be. Does the river of time flow continuously, or is it actually a series of discrete, indivisible moments like the frames of a film? David Finkelstein saw the universe not as a smooth continuum, but as a cosmic computer, ticking with a fundamental granularity. He proposed that spacetime possesses an atomic structure, built from the tiniest possible grains of time he named chronons. A chronon is not just an incredibly small unit of measurement, like a second chopped into infinite pieces. It is the smallest possible step, the ultimate pixel of temporal reality, beyond which no further division is possible. In Finkelstein's spacetime code theory, the universe is fundamentally computational. Reality is not a thing but a process, a vast calculation unfolding at the Planck scale, the very bedrock of physical reality. Time, in this view, is simply the sequential processing of information, one chronon after another. His work demonstrated mathematically how the smooth, continuous spacetime of Einstein's relativity could emerge from this discrete, underlying structure through the principles of quantum logic and algebraic methods. This is like a digital movie, where the fluid motion you see on screen is actually composed of a rapid sequence of individual frames. Your experience of a flowing, continuous reality is an illusion generated by the breathtaking speed of the cosmic processor. This perspective offers a startlingly clear explanation for why time has a single, irreversible direction. Computational processes are inherently sequential and irreversible. A computer cannot unrun a calculation, it can only proceed to the next step. The arrow of time might be nothing more than the universe executing its code, line by line. This powerful intuition has blossomed into contemporary approaches to quantum gravity, most notably causal set theory. This framework builds spacetime directly from discrete events, like beads on a string, connected only by fundamental cause and effect relationships. The smooth geometry of space and the flow of time are secondary, emergent properties of this underlying network of causal links. This granular nature of reality might even resolve ancient philosophical puzzles like Zeno's paradoxes, which questioned how an arrow could ever reach its target if its flight was infinitely divisible. If time is discrete, the arrow simply moves from one chronon to the next, without needing to traverse an infinite number of points. The universe operates in finite steps. Finkelstein's computational view transforms time from a river into a processor, and information becomes the most fundamental currency of existence. This naturally leads us to the quantum information approaches that see the cosmos as a vast, evolving quantum computer. Zurek watched a quantum particle, a shimmer of pure possibility, and asked a simple question: why does it ever become a single, definite thing? His answer, quantum Darwinism, reveals that time's arrow is born from the relentless copying of information. In the fragile quantum realm, a particle exists in a superposition of many states at once. But it never exists in isolation. It is constantly buffeted by its environment, by stray photons and air molecules that constantly measure it. Zurek realized this environmental monitoring is not destructive noise. It is a process of natural selection for information. The states of the quantum system that are most robust, that can survive this constant interaction, are the ones that get copied over and over again into the environment. Think of a stone dropped into a pond. The splash is the quantum event, a brief moment of many possibilities. The ripples spreading outward are countless copies of one specific piece of information, the location and time of the splash. Anyone anywhere on the pond can look at the ripples and deduce that a stone was dropped. They do not need to see the stone itself. This proliferation of information is quantum Darwinism in action. The world we perceive as classical and definite is simply the set of quantum states that have successfully reproduced their information imprinted on the environment in 1,000 different ways. This process carves the arrow of time into reality with stunning clarity. Information proliferation is fundamentally irreversible. You cannot uncopy a file, unsend a message, or unmake a ripple. Once the environment has learned a fact about the quantum system, recording it in countless photons and atoms, that fact becomes a permanent part of the past. This is why we remember yesterday but not tomorrow. The past has been redundantly recorded in the world around us. Trillions of environmental interactions have fossilized it into reality. The future, however, remains unrecorded, a cloud of potentialities not yet copied and solidified. Zurek's framework weaves together the different arrows of time into a single, elegant tapestry. The thermodynamic arrow, the increase of entropy, is driven by this irreversible spreading of information. The cosmological arrow, the expansion of the universe, provides the ever-growing arena where this information can proliferate. And our psychological arrow, our unshakable sense of a flowing present, is our conscious experience of this continuous process of information copying and selection within our own brains. Laboratories are now testing these ideas, watching quantum systems decohere into classical definiteness, and they see the predictions of quantum Darwinism borne out. The emergence of time itself in theories of quantum gravity may be this very process, the universe learning about itself through interaction, one irreversible copy at a time. This profound link, where information is the ultimate substance from which time is forged, points directly to a principle where information is not just in space, but where space and time themselves are made of it. Gerard T. Hooft envisions a cosmos that ticks like a perfect, unfailing clock. This Nobel laureate proposes a universe that is fundamentally deterministic, a cosmic cellular automaton where time emerges from the sequential updating of reality at the smallest possible scale, the Planck length. Imagine a vast, infinite grid where each cell can be either on or off. The state of the entire grid updates in discrete, rhythmic ticks, with each cell's new state determined by a fixed set of rules applied to its neighbors. For T. Hooft, our universe, with all its stars, planets, and conscious beings, is the breathtakingly complex pattern that emerges from this underlying, pixelated computation. There is no true randomness in this view, only the illusion of chance created by our limited, coarse-grained view of the system. We are like someone watching a movie, seeing only the actors on the screen and not the digital code that generates each frame. The apparent probabilities of quantum mechanics are not fundamental, but simply reflect our ignorance of the hidden variables, the precise on or off states of the cosmic grid at the deepest level. In this framework, time is nothing more than the relentless progression of these computational states. The arrow of time finds a natural and powerful explanation here. Information processing is inherently irreversible. A computer cannot unrun a calculation. Once a logic gate flips from a 0 to a 1, that step is final. It cannot be undone without adding new information, without performing another computation. This mirrors the second law of thermodynamics perfectly. The universe, as a computer, is constantly moving from one computational state to the next, and it cannot go back. This provides a clean, logical basis for why we remember the past and not the future. The past is the set of computational steps that have already been processed and recorded. T. Hooft's bold challenge to conventional quantum mechanics offers a potential solution to the infamous measurement problem. In his deterministic view, the act of measurement is not a magical collapse of a wave function. It is simply the process by which our macroscopic instruments, which are themselves part of the automaton, become correlated with the underlying deterministic state of the system being measured. The definite outcome was always there, encoded in the hidden variables. While controversial, this perspective is gaining fresh attention in quantum foundations, where a growing number of physicists are seriously considering that the bizarre probabilities of the quantum world might be an approximation of a deeper, deterministic reality. This computational hypothesis forces a profound question about our own place in this cosmic machine. If the universe is a deterministic automaton, then our conscious experience of making free choices, of feeling the flow of time, is itself part of the computation. Your sense of a flowing present may be the experience of your brain, a vastly complex pattern in the grid, processing the sequential updates of the cosmic program. This brings us to the very edge of physics and philosophy, to a theory that places consciousness itself as the ultimate architect of time. Roger Penrose saw the end of all things not as a final silence, but as a transformation. His conformal cyclic cosmology begins where other theories stop, at the heat death of our universe, when all matter has decayed and black holes have evaporated into a thin, cold sea of radiation. In this state of maximum entropy, a strange symmetry emerges. As the universe expands toward infinite size and its temperature approaches absolute zero, it loses all sense of scale. An infinite distance and a zero distance become physically identical. This is the magic of conformal rescaling, a mathematical transformation that allows the endless, featureless future of one universe to be seamlessly reborn as the hot, dense, low-entropy beginning of the next. Our Big Bang was not the absolute beginning. It was the conformal continuation of a previous eon's infinite future. In this grand cycle, time has no true start or finish, but its arrow is reset with each new birth. As one eon dies in a state of maximum disorder and infinite scale, its information is effectively erased. The specific details of its history, the positions of every particle, are lost in the transformation. This cosmic forgetting is what creates a clean slate, a new state of incredibly low entropy from which a new arrow of time can emerge. The universe forgets its past to have a future. This elegantly solves the puzzle of our own universe's improbable beginning. We don't need to explain why the cosmos started in a special, ordered state. It simply inherited that state from the conformal death of its ancestor. Penrose has searched for the ghost of that previous eon in the oldest light we can see, the cosmic microwave background radiation. He and his collaborators claim to have found faint, concentric circular patterns imprinted in this radiation, which they interpret as the ripples of colossal gravitational waves generated by the collision of supermassive black holes in the universe before ours. These are the final echoes of a long-dead cosmos, whispering its story into the fabric of our own. While this evidence remains hotly debated, the vision it supports is staggering. We may be living inside the cosmic aftermath of another reality's end. This endless cycling of creation and dissolution, where time's arrow is perpetually reborn, resonates with ancient philosophical ideas of the eternal return found in Hindu cosmology and Stoic thought. The universe breathes in and out forever, and with each exhalation, a new temporal reality is born. Penrose's cosmology offers a profound perspective, one where time is both eternal and perpetually new. If the very fabric of the cosmos undergoes such a radical reset, then the flow of time we experience may be a deeply local phenomenon, a single chapter in an infinite book. This cosmic perspective on the origin of temporal direction brings us to the final and perhaps most intimate frontier, the relationship between the flow of time and the conscious mind that observes it. Julian Barber invites you to step outside of time entirely, into a realm of pure possibility he calls Platonia. This is not a physical place, but a timeless, abstract landscape containing every single, instantaneous configuration our universe could ever possibly be in. Every arrangement of every atom, every possible pose of reality, exists here eternally. In Barber's radical view, time is not a river flowing through these states. It is a complete illusion. What we perceive as the flow of time from past to future is actually just our consciousness hopping from one of these static nows to a very similar one in the vast landscape of Platonia. Think of a stack of photographs of a tree throughout the seasons. Each photo is a complete, frozen moment, a single now in Platonia. The photo of the tree in full bloom exists just as permanently as the photo of its bare winter branches. There is no motion between them in the stack. Yet, when you flip through the photos in sequence, you get the powerful illusion of a single tree growing and changing. Barber suggests our reality works the same way. Your life is not a movie, but a carefully selected series of still frames. The feeling of movement, of cause and effect, arises because each now you experience is strikingly similar to the one before it, with only tiny differences. This elegantly dissolves ancient puzzles like Zeno's paradox, which questioned how an arrow could ever move if its flight was composed of an infinite number of frozen instants. For Barber, the arrow never moves through time. It simply has different, timeless positions in different nows, and our consciousness strings those positions together to create the story of its flight. The big question then becomes, what governs the sequence? Why do we experience this particular, ordered series of nows that creates a consistent history? Barber proposes a fundamental law, a rule that prefers sequences where successive configurations are related by what physicists call a timeless equation. It is the geometry of Platonia itself, the relationships between the points in this landscape, that makes some paths through the nows more natural and likely than others. This timeless approach is more than a philosophical curiosity. It provides a powerful way to tackle the infamous problem of time in quantum gravity, where time simply vanishes from the fundamental equations. If Barber is correct, then your deepest feeling, the sensation of time passing through you, is the most persistent and convincing illusion there is. This forces a confrontation with the final mystery. If reality is fundamentally timeless, then what is consciousness? And why does it craft such a vivid and unshakable story of past, present, and future from a landscape of eternal stillness? Max Tegmark's cosmos is one where numbers breathe life into reality itself. He proposes a stunningly elegant idea, the mathematical universe hypothesis. In this view, our physical reality is not merely described by mathematics, it is mathematics. Every consistent mathematical structure physically exists, and our universe is just one specific, incredibly complex equation playing itself out. Within this eternal, abstract landscape, time is not a fundamental river. It is a convenient coordinate, a parameter like the x-axis on a graph, useful for navigation but devoid of any intrinsic flow. The relentless passage we feel, the march from past to future, is an illusion generated from within. We are self-aware substructures inside the grand equation, and our consciousness reads the sequence of our internal states as a flow. Think of a novel. The story has a beginning, middle, and end, but the book itself is a static object. The pages do not turn themselves. Your act of reading, moving your eyes from one word to the next, creates the illusion of a narrative unfolding in time. In Tegmark's universe, you are both the reader and a character in the book, and your perception of time is simply you reading the mathematical story of yourself. This perspective reframes the arrow of time not as a cosmic law, but as a consequence of how information is processed and stored within the structure. Our brains are biological machines that record memories, and that recording process imposes a one-way direction, creating the story of a past that is fixed and a future that is open. This radical view offers a breathtaking solution to the fine-tuning problem, the puzzling observation that the universe's constants seem perfectly calibrated for life. If all mathematical structures exist, then we simply find ourselves in one that is complex enough to contain self-aware observers who can ask the question. There is no fine-tuning, just a statistical selection effect. Our profound ability to describe the cosmos with mathematics is no longer a mystery, it is a tautology. We are mathematics discovering itself. This vision, where time dissolves into an eternal, equations reality, resonates deeply with Eastern philosophical traditions like Buddhism and Taoism, which have long contemplated the illusory nature of temporal passage. If Tegmark is correct, then the search for time's ultimate nature might be a search for the most fundamental algorithms of existence, pointing toward a universe that is not just mathematical, but computational in its very essence. Seth Lloyd calculates that since its birth, the cosmos has executed 10 to the power of 120 elementary logic operations. This is not a metaphor. The quantum engineer proposes that the universe is not merely like a computer. It is a computer, a vast quantum system processing information at the fundamental scale of reality. In this computational universe, every collision of particles, every emission of a photon, is a quantum computation. And what is time in this view? Time is simply the tally of these operations, the sequence of processing steps the cosmic machine has executed. The relentless forward march we experience as time's arrow finds a beautifully simple explanation here. Most computations are logically irreversible. When a computer gate flips a bit from a 0 to a 1, that step is final. To reverse it, you would need to perform another computation, using more energy and creating more information. This mirrors the second law of thermodynamics perfectly. The universe, as a computer, cannot unrun its own code. It can only move forward to the next logical operation, and in doing so, it permanently records its past states in the ever-growing ledger of reality. This is why we remember yesterday but not tomorrow. The past is the set of computations that have already been processed, and their results scattered throughout the cosmos. Lloyd has demonstrated how foundational physics emerges from this principle. The strange probabilities of quantum mechanics, the inevitable rise of entropy, even the properties of black holes, can all be seen as natural consequences of the universe computing its own state. This vision finds a powerful echo in the latest quantum gravity research, where spacetime itself is thought to emerge from a dense network of quantum entanglement, a structure that looks very much like the wiring of a colossal quantum processor. If this is true, then the flow of time is directly tied to the universe's computational capacity. It is not an independent river, but the processing speed of cosmic reality. The ticking of every clock is just a local echo of the universe executing its fundamental algorithm, one irreversible quantum calculation at a time. Lee Smolin sees the universe not as a static kingdom ruled by eternal laws, but as a living, breathing entity whose very rules change with time. He calls this temporal naturalism, a philosophy that places time itself as the most fundamental reality. For Smolin, the laws of physics are not timeless mathematical truths inscribed at the beginning. They are more like habits, patterns that have evolved and solidified over cosmic epochs through a process of cosmological natural selection. In this radical view, the arrow of time is not something that emerges from deeper physics. It is primitive, a fundamental aspect of existence, with causation being the bedrock upon which reality is built. This turns the traditional scientific view completely on its head. Instead of timeless laws governing a changing world, it is the flow of time that gradually forges the laws we observe. Smolin provides a stunning mechanism for this evolution: black holes as cosmic wombs. He proposes that every black hole in our universe could be the seed for a new baby universe, budding off into its own space-time continuum. Crucially, these offspring would not be perfect copies. The fundamental constants, like the strength of gravity or the mass of an electron, would be slightly tweaked, mutated in the birthing process. This sets up a grand cosmic Darwinism. Universes that produce more black holes have more offspring, passing on their physical laws. Our universe, with its remarkable capacity for forming stars, galaxies, and ultimately black holes, is not a miracle of fine-tuning. It is a cosmic success story, a universe whose laws were naturally selected for their fecundity. This elegantly explains why we find ourselves in a cosmos so hospitable to the complex structures that allow for time's flow. The very laws that give us an arrow of time are the same laws that efficiently produce black holes, making our universe a prolific ancestor in a vast, branching multiverse. Smolin's ideas remain provocative, challenging the core of how we do physics, but they offer a compelling narrative for why time feels so real and irreversible. If the laws themselves are aging and evolving, then the stage of reality is not fixed, and the play is still being written. This concept of a changing physical reality pushes us to the final frontier, where time may not just be evolving, but could be a collective illusion woven from countless individual perspectives. Carlo Rovelli invites us to consider a universe where time is not a backdrop but a story told by heat. In his thermal time hypothesis, the flow of time we feel so deeply is not a fundamental river, but a side effect of thermodynamics, emerging from the statistical imbalance of quantum states. Imagine a cup of coffee cooling in a quiet room. The heat flows from the hot cup into the cooler air, and this irreversible process defines a clear direction, a before and after. Rovelli proposes that this is the essence of time. For any given physical system, its particular state defines its own unique flow of time through a mathematical structure called the modular group of its observable algebra. This is a technical way of saying that time is a local and personal affair, generated by a system's internal state and its interactions with everything else. Standard, uniform clock time only emerges when systems are in a state of thermal equilibrium, like the coffee and the room air finally reaching the same temperature. At that point, the statistical fluctuations even out, and time appears to tick along predictably. This elegantly explains why time seems so solid and dependable for large objects like planets and people, which are in approximate equilibrium, while it behaves so bizarrely in the quantum realm or near a black hole, where equilibrium is shattered. Ravelli's work is deeply tied to his development of loop quantum gravity, a leading approach to unifying general relativity and quantum mechanics. In that fundamental theory, time vanishes completely from the core equations. There is no T for time. The thermal time hypothesis is the breathtaking proposal for how time re-emerges at the scales we experience, statistically, from a timeless underworld. This means the arrow of time is not universal. A system far from equilibrium, like a collapsing star, could experience a radically different temporal flow compared to the placid time of empty space. Your own consciousness, a highly ordered and non-equilibrium system, might be weaving its own unique temporal thread. This state-dependent nature of time forces a profound shift, suggesting that time is not a single universal stream, but a vast, shimmering network of interrelated nows, each born from a specific perspective. Albert Einstein spent his final years in a quiet Princeton study, consumed by a dream that would forever elude him. He was not trying to add another equation to physics, but to rewrite its entire foundation with a unified field theory. His vision was breathtakingly ambitious. He believed that time and space should not be treated as separate stages. Instead, they must emerge together, intertwined from a more primitive, pre-geometric reality. In this view, matter and energy are not things placed within space-time. They are manifestations of its curvature, geometric expressions of the cosmic fabric itself. Einstein was convinced that the mysterious arrow of time, the relentless one-way direction we all experience, should not be an added assumption. It must be a consequence, something that naturally falls out of the fundamental field equations governing this unified reality. His unpublished notebooks are filled with explorations of how time might be intrinsically linked to electromagnetic phenomena, searching for a geometric origin for time's flow. This grand quest did not die with him. It lives on in the most advanced frontiers of theoretical physics. String theory, for instance, treats time as one of the many dimensions woven into the fabric of its tiny, vibrating strings. Loop quantum gravity, in contrast, often finds time disappearing from its core equations, only to re-emerge as a statistical property of a vast quantum network. There is a growing sense among many physicists that Einstein's deepest intuition was correct, that time is not a fundamental ingredient but an emergent phenomenon. The holographic principle offers a stunning modern realization of this idea. It suggests that our four-dimensional universe, complete with the flow of time, is a projection from a two-dimensional surface of quantum information, much like a three-dimensional hologram emerges from a flat piece of film. Space and time are not the foundation, but the consequence. Einstein's unfinished work stands as a powerful monument to the humility of science. It reminds us that our understanding of something as basic as time remains profoundly incomplete. His dream pushes us to ask how we could ever test such a radical idea. How to move from beautiful mathematics to observable proof in our quest to understand the ticking of the cosmic clock. A laboratory in Vienna holds its breath as a single photon is measured, its fate entangled with a partner across the room in a delicate quantum swap. This is not just an experiment in communication, it is a direct test of time's deepest symmetries. Recent tests with entangled particles have delivered a startling result. At the microscopic level, quantum mechanics appears to be perfectly time-symmetric. The equations work just as well forward as they do backward. A quantum handshake looks identical, whether you view it as an offer from the past or an echo from the future. This suggests that the relentless forward drive of time we experience is not written into the quantum source code. Meanwhile, in massive particle accelerators, physicists are scrutinizing the behavior of neutral mesons, particles that oscillate between matter and antimatter. Here, they have found a tiny but crucial crack in the mirror, a phenomenon known as CP violation. There is a minuscule preference for these particles to decay into matter over antimatter. This asymmetry, imprinted into the laws of particle physics, might be the very reason anything exists at all. It could be the seed from which the cosmological arrow of time grew, the original bias that tipped the scales of the early universe toward the world of structure we inhabit. Even the hallowed second law of thermodynamics is being probed at the nanoscale. In exquisite experiments with tiny beads in fluid, scientists have watched as thermal energy spontaneously organizes, causing a bead to momentarily defy the flow of time and move uphill. These are not perpetual motion machines, but statistical fluctuations, momentary reversals that prove the arrow of time is not an unbreakable law, but an overwhelming probability. For a split second in a system small enough, the universe forgets which way is forward. The next frontier is even more profound. Future experiments with ultra-sensitive quantum gravity detectors aim to listen for the faint ticking of spacetime itself, hunting for evidence that time is not a smooth flow but a series of discrete steps, Chronons at the Planck scale. If they succeed, they will have found the pixels of reality. Each of these experimental paths, from the quantum to the cosmic, is gradually answering the central question: is time's arrow a fundamental feature of the universe, or is it an emergent property, a story that coalesces from countless interactions? This concrete evidence from the lab bench forces us to confront the final and most personal layer of the mystery, the philosophical weight of a universe where time may be a story we tell ourselves. The final implications of these forgotten theories ripple far beyond the equations, into the very heart of what it means to be human. If the direction of time is not a fundamental feature of reality, then our deepest convictions about free will and moral responsibility begin to waver. How can you be truly responsible for an action if the future is already written in a timeless block? Or if your choice is merely the effect of a future cause pulling backward through the quantum void? The self you believe to be a continuous entity, a single character in the story of your life, might be a fragile illusion. Your personal identity, built on the chain of memory, could be a temporary alignment of countless nows, with no more substantial connection than adjacent frames in a film. This directly challenges the linear causality that underpins our entire legal and ethical systems. If backward time influences are real, as Wheeler and Cramer suggest, then punishing a cause for its effect becomes a philosophical hall of mirrors. Eastern traditions have contemplated this for millennia. The Buddhist doctrine of dependent origination, which sees all phenomena as interconnected and lacking independent existence in a flowing present, finds a startling echo in the relational and emergent time of modern physics. Both point toward a reality where the solid self and the river of time are projections of a deeper, timeless interdependence. Even our most intimate experiences of memory and anticipation need re-examination. If the past and future are not fundamentally different from the present, then remembering is not retrieving a fixed record, but actively participating in the unfolding of a holographic reality. Anticipation is not peering into an empty future, but feeling the pull of quantum potentials from a reality that already exists in its entirety. These are not abstract puzzles. They are urgent questions about the nature of our own consciousness and its role in crafting the reality we perceive. The journey through these 28 forgotten theories reveals that our greatest challenge is not just to discover the laws of physics, but to integrate that knowledge with the profound mystery of our own experience. This forgotten treasure trove of ideas holds the potential to ignite the next revolution, forcing a unification of the objective and the subjective to finally answer the ancient question: why does time seem to flow, and what are we within its current? These scattered clues from physics' forgotten past are not dead ends, but pieces of a puzzle waiting to be assembled. A future revolution in physics will not come from a single equation, but from a grand synthesis, weaving these 28 threads into a new tapestry of time. In this emerging vision, time is not a fundamental stage on which the universe plays out. It is an emergent phenomenon, a story that coalesces from three profound sources: quantum information, thermodynamics, and consciousness itself. Each operates at a different scale, creating distinct arrows that miraculously align. At the microscopic quantum level, time's direction might be born from the irreversible proliferation of information, as Whitehead's quantum Darwinism suggests. Every interaction between a particle and its environment creates a copy, a record that cannot be uncopied, setting a local direction for cause and effect. At our human scale, the thermodynamic arrow takes over, driven by the overwhelming statistical push toward disorder that Prigogine saw as the engine of complexity. And on the cosmic scale, the gravitational pull of all matter in an expanding universe, as Sciama envisioned, provides the master clock, the cosmological arrow that orients all the others. The true mystery is not why time has a direction, but why these three distinct arrows all point the same way, creating the single, coherent river of time we all experience. A complete theory explaining this alignment would be one of the greatest achievements of science. It could resolve physics' most stubborn puzzles. The infamous measurement problem in quantum mechanics, where a particle's possibilities collapse into one reality, might simply be the moment a quantum arrow is amplified by a thermodynamic one, as a measuring device turns a fragile possibility into a permanent record. Even the nature of dark energy, the mysterious force accelerating cosmic expansion, could be understood not as a new force, but as a consequence of the universe's evolving information content and its relationship to the emergent flow of time. This synthesis points toward an even deeper connection, one that ventures into the realm of mind. Consciousness itself may be the ultimate expression of this aligned temporal flow. Your subjective experience of a flowing present could be how a complex, self-organizing system like your brain processes and integrates these different arrows, from the quantum vibrations in your neurons to the thermodynamic rhythms of your body. You are not just observing time, you are the experience of these arrows aligning within you. This revolution demands we let go of time as an intuitive given. It is something far richer and more mysterious, a layered reality where quantum handshakes, dissipating heat, and the gaze of a conscious observer all conspire to create the undeniable now. As we prepare to conclude, this integrated vision forces us to confront the final, most personal implications of a universe where time is not what it seems. Our journey through these forgotten pathways reveals a universe where time is far stranger than a simple river flowing to the sea. We have seen it as a statistical illusion in Boltzmann's gaze, a creative process in Whitehead's philosophy, and a thermal ghost in Ravelli's equations. From Smolin's evolving laws to the quantum handshakes of Cramer, a stunning possibility emerges. Time may not be a fundamental stage at all, but a story that coalesces from deeper, more primitive ingredients. It appears to be emergent, bubbling up from the quantum entanglement of countless particles. It is relational, meaning your now and the now of a distant star are not the same absolute moment, but personal perspectives in a vast network. From certain mathematical viewpoints, like Barber's Platonia, this relentless flow could be the most persistent and convincing illusion of all. Yet, the feeling is undeniable. The memory of your first day of school, the anticipation of a meeting tomorrow, this visceral sense of a moving present is the very fabric of our conscious lives. This is the ultimate challenge any theory of time must face. It cannot remain a set of cold equations. It must also explain the warmth of experience, the undeniable reality of a moment that feels like now. The potential locked within these abandoned ideas is staggering. They might finally weave quantum mechanics and general relativity into a single, coherent tapestry, explaining why gravity curves space and particles exist in clouds of possibility all at once. They could pinpoint the origin of time's arrow, not as a mystery, but as a natural consequence of a universe learning about itself. Some even dare to suggest that these theories could illuminate the nature of consciousness itself, explaining why a thinking mind inherently experiences a flowing time. The physicist John Archibald Wheeler once remarked that time is nature's way of keeping everything from happening at once. These 28 forgotten theories begin to reveal the profound machinery behind that simple phrase. They show us that time is the universe's most sophisticated and elegant trick, and we are only just beginning to learn how it is done. We would love to hear which of these strange ideas about time resonates most deeply with you. Share your thoughts in the comments and subscribe for more journeys to the edge of understanding.